So I want to point out here that we have on Earth, we know that the acceleration due to gravity is generally 9.8 meters per second squared. But then if you look at this diagram, you'll notice that there's a whole bunch of different weights. So if you didn't know already, it turns out that the Earth is actually not perfectly round. And because of that, we have from the center of the Earth, we have a greater distance depending on where you're at. So at the equator, it turns out that radial distance is actually larger than at other places. Now, as a result, if we take a look, if we're looking at the force due to gravity between any two objects, we have two ways to consider that. If we're near the surface of a planet, so in this case, we're going to be specifically talking about planet Earth. If we are near the surface, we know that we have that weight force, and that has to be equal to the universal force of gravity between two objects. So here, notice I have the mass of the object on the surface. I have the mass of Earth, okay? And then this is going to be equal to the weight force. And then here, I have the radius of the Earth plus the altitude. Now, if you are on the surface of the Earth, right, your altitude is 0. So for this part, when I'm looking at the universal force due to gravity, it's just going to be the radius of the Earth on the bottom here. Now, taking a step back then, if I'm comparing this acceleration due to gravity, this g right here, and I'm taking a look at the relationship between the distance from the center of the Earth, you'll notice it's an inverse square relationship. So the greater the distance, the smaller the gravitational acceleration is going to be, okay? So a new concept that we don't really cover too much in AP1, but you'll talk about it more if you take APC, is the concept of a gravitational field. And what that is it's a region in which a mass experiences a force due to gravitational attraction. And what happens is we have different fields as we get further and further away from the Earth, okay? And specifically what we want to look at is something called the gravitational field strength. So if you notice in the diagram, we had here, instead of meters per second, we had newtons per kilogram. And the reason why we have that is because the gravitational field strength, G, which is the acceleration due to gravity, but it's also the gravitational force per unit mass that is put onto any body placed at any point, okay? So with that said, let's take a look again at this G value, okay? If we're looking at our weight force, so our force due to gravity, we know that it equals mass times acceleration by Newton's law, so solving for G, we get Fg over m, okay? But what we want to do is instead of this force due to gravity, we want to relate that to the gravitational force between any two objects. So if we replace this with F big G, then we have this equation, the m's cancel out, and then we're left over with this G equal to big G, big M over R squared. So this particular equation, the time that you're going to be looking to use this is when we are considering the acceleration due to some sort of gravitational force. So if we're looking for acceleration and we're considering the relationship between any two objects, we can go ahead and use this if that object is small enough, okay? So let's take a look at example number 1. We have a moon. It's giving us the mass, it's giving us the radius, and we want to find the gravitational field strength. So again, gravitational field strength, when you hear that, we're really looking at the acceleration due to gravity, or specifically how much force is put on any unit of mass. So we're going to go ahead and use this equation when that comes up. So G on the moon equals big G mass of the moon over R squared, the radius of the moon. And all we have to do here is plug and chug. So we get 7.36 times 10 to the 22nd kilograms. So that's my mass. Let's put in this G here. It's 6.67 times 10 to the negative 11 meters cubed per kilograms times second squared. And that's over the radius, 1.74 times 10 to the 6th meters. And then when you type that on your calculator, if you do it correct, you should get 1.6. Okay, now at this point, we have an option of units that we could use. We can either use newtons per kilogram, which kind of makes sense when we're talking about this sort of strength here, or you can use meters per second squared. I have no preference, and you will not be marked incorrect for using any units that correspond with acceleration. So I'm going to use newtons per kilogram, but meters per second squared is totally fine. Same thing. All right, so for example 2, we have planet X. It has free fall acceleration, so at the surface, okay? Planet Y has twice the mass and twice the radius of planet X. So we have planet Y, but we're comparing it to the mass and the radius of planet X, and we're trying to find out what this new free fall acceleration is at the surface. So we can go ahead and set up a ratio. So if I have the free fall acceleration on X, I know that that's going to be equal to the gravitational constant times the mass on X divided by the radius on X squared. Now g of Y, in comparison, g is going to be the same, it's a constant, but the mass is twice as much. So it's twice as much as the mass on X. And the radius is also twice as much. So for the radius, I'm going to have twice the radius quantity squared. But you got to remember, if we're squaring that radius, that's equivalent to 4r squared. Okay, so doing some algebra here, we're going to start canceling some things out. So for this, the g's cancel out, the m's cancel out. We're going to ignore this and use our 4r squared, so the r squareds cancel out. So notice on top, everything divides away, and so on top, what's going to happen is we're going to be left with 1. On the bottom, we're left with 2 over 4, because remember, this 2r quantity squared is represented by the 4r squared here. 2/4 is 1/2. At this point, I can go ahead and cross multiply. So my acceleration due to gravity on planet Y is going to be gy times 1, which is just gy, equal to 1/2 times gx. Now the convenience of this problem is gx is 8 meters per second squared. So that's 1/2 times 8 meters per second squared. And that's going to equal 4 meters per second squared. And the last example for this page, we have acceleration due to gravity in space. All right, so you and the sun have been transported to an alternate universe in which there is no other matter. Okay, so can anybody tell me why is it an issue if there was matter? Why would that be a problem? Yeah, because you would be attracted to everything in the way. So if we're looking at right now the force of attraction between me and the sun, I have moons, I have planets, I have asteroids, I have all these other things that I could possibly be attracted to. And so in comparison, let's even just think about the moon. Think about the distance from us to the moon versus us to the sun. What's going to have the greater gravitational force? The moon. Why? Because it's closer, and we know by the inverse square rule that the smaller the distance, the greater that universal force of gravitation. Okay, so we are luckily in this alternate universe. It's just us and the sun. That's it. Okay, so we want to know what our instantaneous acceleration toward the sun would be if we are already 1.5 times 10 to the 11th meters away from the sun. Okay, so in this case, we can certainly use the same equation, but we're going to have a little bit of a difference here. And the reason why it's going to be different is because we're taking a look at that instantaneous acceleration, but now we have the radius of the sun instead of the earth here, but we have a significant altitude, okay, so that we need to include in there. So what's going to happen is we'll still use G equals GM over R squared, but R is going to be the radius of the sun plus the altitude, and that is going to be squared. So G is 6.67 times 10 to the negative 11th meters cubed per kilograms times second squared. The mass of the sun is 1.99 times 10 to the 30th kilograms. And then we're going to divide that by the radius of the sun, 5.6 times 10 to the 7th meters, plus our altitude, which is 1.5 times 10 to the 11th meters. And then we need to square that. And if you plug that in and type everything in perfectly, then you should end up with 5.9 times 10 to the negative third meters per second squared. Now for this particular problem, you might want to be careful because what I found, a lot of people when they plug this in were getting 0.0006. So you might want to consider changing your calculator into scientific mode so that you can get a more accurate answer in comparison.